So we're now going to turn our attention to what, in my humble opinion, is one of the most interesting aspects of C++ STL, and that's its support for the so-called associative containers. And so associative containers are essentially data structures, they're containers, that support efficient insertion, deletion, and find operations based on keys. And as we'll see, there's a bunch of different variants of associative containers. There's simple associative containers, things like sets. There's pair associative containers, things like maps. There's unique associative containers, things like map and set. There's multiple associative containers that can contain duplicate keys like multiset and multimap. And then there are sorted associative containers and hashed associative containers. And the original associative containers were all sorted, so they're still called associative containers. And then the ones that came later that support hashing are called unordered associative containers. And so sometimes to be more modern looking and more orthogonal, it's probably better to talk about sorted associative containers or ordered associative containers and unordered associative containers. But sometimes you'll see people using the word associative container to mean the ordered associative containers, because those were the ones that came along first. So even some of the later terminology uses that somewhat inconsistent phrasing. So as I mentioned, there's two types of associative containers in STL. The first ones, the ones that have been there the longest, are the ordered associative containers, and they've pretty much been in there since day one. And they support efficient operations on elements using keys that are ordered by the less than operator. So what that implies, of course, is anything you put into an ordered associative container has got to define the less than operation. Now, for obviously for built-in types like int and double and float and long and so on, operator less than is defined just as par for the course. That's what you get with all those built-in types. With user-defined types, you have to define them, or they have to be defined by the people who wrote the implementation. So either way, it works quite easily. As you can see, there are four main ordered associative containers, and those include set and multiset, which only have keys, and then we have map and multimap, which have key value pairs. And the main difference between set and map on the one hand and multiset and multimap on the other is that set and map can only have unique keys, whereas multiset and multimap can have duplicate keys. Under the hood, these containers, these ordered associative containers, are implemented using red-black trees, which are balanced binary trees. And hopefully you studied something about this in a data structures course, but in a nutshell, what they allow you to do is they allow you to have the operation, the asymptotic time complexity for insertion, deletion, and find bounded to be log of n. So if n is the number of elements in the container, then a balanced binary tree will ensure that no operation ever takes more than log n time to run, where n is the number of elements. And the way this works is every time you insert something, then the tree is rebalanced to make sure that that property is preserved. And every time you delete something, the tree is also rebalanced to ensure that the property is preserved. And of course, when you find something, you don't change the tree. So as a consequence, it just takes advantage of the fact that it's always going to be log n, even in the worst case. So that's a nice property. Now, for all these associative containers, unlike the sequential containers we've talked about this far, like vector and dec and list and so on, which had iterators that could actually change the values of the elements that they were iterating over, that obviously is not allowed with the ordered containers, because if you were able to change the values of the keys as you were iterating over them, then the ordering discipline, the ordering protocol that's supported by the binary tree would just completely be ruined very quickly, because you'd be changing values, but you wouldn't be rebalancing the tree and putting things back in the position where they belong. So as a consequence, you'll see when we look at how the implementations work, the keys are always treated as consts, so you can't change them. So iterators to sets and maps and so on always end up with const keys. So you can't touch their value. To quote the MC Hammer song, can't touch this. So then there's also unordered associative containers. And they maintain the data structure using fast associative operations, but they are implemented using hashing as opposed to sorting. So as you can see here, it's basically the mirror image of all the ordered associative containers, except it's unordered underscore whatever, unordered set, unordered map, unordered multiset, unordered multimap. But otherwise, the semantics are the same. Sets and maps must have unique keys. Multisets and multimaps can have duplicate keys, but they're not sorted, they're not ordered, they're done with hashing. And hopefully you again remember what hashing is. The way that this works in STL is they do hashing with a what's called chaining collision resolution. So if two values end up hashing to the same location, like if you look at this example here, you can see that John Smith and Sandra D both hash to location 152 in this array. And what happens at that point is we've got basically a linked list that will do collision resolution by just chaining those things together. And then after we hash, we do a linked list search, a linear search, to see whether or not the item is already in that bucket, the chain that's associated with that bucket. Now, unlike Java hash maps, which do some really cool optimizations in later versions to adaptively replace linked lists and linear search with balanced binary trees and binary search, the STL implementation doesn't do anything quite that clever. And I've never quite understood why, quite frankly, because one of the potential downsides with using hashing is that if you have sort of the worst case behavior where your hash function ends up directing every key to the same location in the hash table, you basically devolve or degrade into linear search, which isn't, of course, what you want at all. But the cool thing about Java is when it starts to detect that that's happening, it'll switch over automatically to use a balanced binary tree. So even in the worst case situation with Java, you end up with basically log n time to do operations amortized. Whereas in STL, they don't quite do that. I've never quite understood why. Maybe it was too much of a pain in the butt to change all the implementations, but it seemed like something that someone should contemplate at some point. As with the ordered associative containers, keys are consts. So once you've put something into the hash table at a certain location, you can't go in there and change the key, because otherwise you'd never be able to find it again, because when you rehashed, you'd end up not being able to locate the bucket, and it would have a different value, and it would just be confusing and wrong. So once again, you got to keep your hands off the values of those keys. Once they're set, you can't change them, although of course you can delete them if you want to, but you can't change them.